Uh, oh, got it. Thank you very much for the introduction and the invitation to speak here. I'm going to talk about using the Wright-Fisher diffusion for statistical inference of evolution. This is work that's in collaboration with nobody. I'm slightly nervous because I don't have any co-authors that I can hide behind for this. This is work I did during a sabbatical I took last year. So I'm very pleased to share it with you. Okay, so some motivations from genetics about why we want to think about diffusion models for evolution. This is a well-known example. I've taken an image from a recent paper by Ian Matheson on modeling lactase persistence. So this is one of the most well-known examples of strong positive natural selection in humans, at least. And we're at the point now where we can sample ancient DNA sequences from humans going back several thousand years, and we can get estimates of the frequency of genetic types of alleles at different time points over this period. So lactase persistence is one of these well-studied examples in which a particular SNP relating to digestion of lactose has been hypothesized to be under positive selection because of its ability to allow adults to digest milk, or to allow humans to digest milk into adulthood. And the questions relating to this mutation relate to how does the spread of this allele relate to the spread of dairy farming, for instance? When exactly did the allele arise? How quickly did it increase in frequency over time? Which parts of Europe did it spread first? How strong is the selection coefficient associated with this allele? So we can get data, and there are very wide confidence intervals over some of the estimates relating to these things. And this paper by Matheson has used some data which is plotted in the top right. And you can see that over a period of around 5,000 years, the allele has increased in frequency from almost nothing in some regions to very high frequency, above 0.6 in Britain and in central parts of Europe. So the question is, given data like this, samples of frequencies of alleles over time, what can we say about something like the strength of natural selection? And so we're going to posit a model, one of whose parameters is the selection coefficient. And Matheson has, in this example, estimated selection coefficients in different parts of Europe, potentially allowing the selection coefficient itself to change over time. And the estimates are in the region of 2%, which by human standards is very strong selection. Just to give a second example, this is taken from Gutsenkunst et al. Again, we're given samples of DNA sequences. This time, the samples were only taken from the present day, so they were able to sample alleles from large swathes of the genome, taking samples from different parts of the world. So they have samples in the left example where they're modeling the expansion of humans out of Africa. They've written down a very simple model. Well, I say simple, but it already has about 12 or 14 parameters or so, parameterizing things like ancient population sizes, the timing of the emigration event, the rate of growth of different populations, the rates of migration. And they've taken samples from Africa, Europe, and East Asia, and potentially just given samples of allele frequencies, they can jointly infer from a model that they write down the estimates of the values of all of these parameters. So even though they have only got data from the present day in this particular example, you can still think of it as if it's a time series model. You just need to run time in reverse if you imagine a diffusion running through the branches of this tree. So you can still think of this as a time series model in some respects. And to emphasize that thinking about time series data, genetic time series data, has become quite popular. I mean, 20 years ago, time series data, at least in humans, was much harder to get hold of. These days, there are more and more studies, and I should probably update this slide, it only goes up to 2020, trying to infer evolutionary parameters from time series data. And of course, it's not just humans. In some other species, it can be easier to obtain time series data, depending on the time scale that you're looking at. So in humans, usually we're thinking over timescales of thousands of years, but there are well-known experiments breeding fruit flies, the Lenski experiment, bacterial evolution, where the timescales can be much shorter, of the order of days or weeks. Potentially, we can use the same models depending on what sorts of parameters are involved. So let's move towards trying to write down a model for changes in allele frequencies over time. And this is a kind of idealized version of what the statistical problem is going to be. So in this cartoon example, we've taken samples of two different alleles, which I'm going to call the red allele and the white allele, at two different times. And these are estimating the true underlying frequency of one of the types at those times. So in this case, the white allele originally had frequency X, and it moved to having frequency Y a time t later. And we've taken a sample of 13 individuals at the first time and a sample of 26 individuals at the second time. And these are giving us noisy estimates of X and Y. So to a statistician, this is a kind of familiar problem, modulo all of the model details. A statistician would call this doing static parameter inference given discrete and noisy observations from a time series model, in particular a nonlinear, non-Gaussian, continuous time hidden Markov model. And that means there are some standard statistical machinery available to us, potentially, for doing inference from this kind of model. So the question really, before we actually do any inference, is which model should we use in such a way that we can set this up to potentially do realistic inference. And I'm not going to do any inference today. I'm really just going to talk about how we can set this problem up properly so that inference is possible. So the model that we use will depend on what we think are the important parameters of evolution, or the important processes that are going on in evolution that we ought to include in our model. And I'm only going to talk about models for which random genetic drift plays an important part. And there are populations and there are timescales where drift is maybe not important relative to selection. And this is not the appropriate model. But whenever genetic drift is appropriate, this is the sort of model we might like to write down. So this is about the simplest stochastic model of a population evolving that we can think of, and this goes by the name of the Wright-Fisher model, in which we have a fixed population size of capital N individuals evolving in discrete generations, and each generation is just going to be formed from the previous one by choosing parent-offspring relationships uniformly at random with replacement. So here I've started with a population in which we have 4 red parents and 6 white parents. And I'm going to form the next generation by going through each of the capital N offspring and picking a parent uniformly at random. And that means some of the offspring will have red parents, some of the offspring will have white parents. And the frequency of the red allele that we might be interested in tracking is going to fluctuate generation by generation. So the stochastic process of interest, whose properties we would like to infer, is the frequency of one of the types, let's say the red type, as it changes in generation k. And in this model, that frequency will take values in 0, 1 on n, 2 on n, and so on, up to 1. This is a model which has only genetic drift in it, essentially. And so we might like to think about other evolutionary and biological parameters that we'd like to include in this model. So we can go back to this model and start, so before I say that, how do we update generation by generation? So the distribution of the frequency is just given by a binomial distribution. This follows from the fact that we're picking parents uniformly at random. So each parent is an independent Bernoulli trial, and the success probability, the probability of getting a red parent, is given by its frequency in the parental generation. So iterating this over generations, in principle, is straightforward. Because it only contains drift, we might like to embellish the model further and incorporate some other biological processes. One of them will be selection, in which we pick a parent not uniformly at random, but in proportion to its fitness. And so to describe the fitness of the parents, we need an additional parameter W, which is capturing the difference in propensity for white parents to have offspring relative to red parents. And that changes the success probability in my binomial distribution, so that the success probability now is proportional to the total fitness of the red parents rather than just uniformly at random. So given our one extra parameter, now we have a Wright-Fisher model with selection, and we can potentially do inference on that parameter. There's one more process that I want to introduce into this model, and that will be as far as I go in terms of the complexity of the model. We'd also like to allow for ongoing or recurrent mutation events during reproduction. So mathematically, what that's going to mean is that with some probability, again, an extra parameter of the model, let's call it mu1, a white parent has a red offspring. And with probability mu2, a red parent has a white offspring. So there aren't any examples in this picture, but you can imagine that we can allow for a difference between the parent and the offspring's type. And that again changes the success probability. The probability that I get a red offspring is now given by the probability that I pick a red parent and it did not mutate, plus the probability that I picked a white parent and it did mutate. But again, the mechanics of the model work very straightforwardly. We can iterate this over generations, and potentially we can do inference on now. We have 3 parameters, the selection coefficient and 2 mutation parameters. And implicitly also we have the size of the population, capital N. Now, working with this model, computationally it gets quite difficult very quickly. What we would really want to do would be to do something like integrate over all the possible paths that the frequency could have taken, the trajectory of the frequency going over generations. And that means essentially kind of integrating over lots of iterated binomial distributions. That gets a bit cumbersome very quickly, and also fully capturing everything that could happen in the model is giving all possible events within the model equal importance. So a further assumption that is common to make is that the population size is very large. And under that assumption, we can start to think about taking a scaling limit of the model, which captures its important features and throws away events which are unlikely when the population is very large. So formally, we're going to take a scaling limit, and that means taking the Wright-Fisher model as a stochastic process. And the only change I need to make to it is to rescale time. So instead of looking over k generations, I'm going to look over t, I'm going to have a new timescale t, which is measured in units of n generations. And the reason for doing that is that we're going to send n to infinity, so the population size becomes infinite. If I just sent n to infinity, there would be no stochastic fluctuations in the model left to happen. By a kind of law of large numbers argument, the whole thing would become deterministic. So if I simultaneously look over longer and longer timescales as I send n to infinity, I will get a non-trivial stochastic limit, which is now a continuous time stochastic process, which is tracking the frequency of the red allele over continuous time. And there are lots of nice convergence results that tell me that the Wright-Fisher model, so rescaled, will converge in a nice pathwise sense to a diffusion model, which is obviously known as the Wright-Fisher diffusion. And the diffusion itself goes all the way back to Fisher in about 1922, and Wright and Kimura and others have studied this model in detail. So the picture of what's happening is I have my population size n, and I have to look over a number of generations of order n. And now I start to send n to infinity. So the population size is getting larger, and the time scale over which I'm looking is getting longer. So I'm kind of zooming out on this picture. And in distribution, the trajectory of the frequency of one of the types that I'm tracking, here the red type, converges to a diffusion process. So it's a continuous time process with continuous sample paths, and it has nice properties that we would expect. In particular, it's a Markov process. And by studying the diffusion as the model rather than the underlying Wright-Fisher model, mathematically, in some respects, it becomes much more tractable. And also, we find that the particular details of the original discrete model tend to matter less, in the sense that we could have started with some other discrete model, taken a similar scaling limit, and we would still have ended up at the same Wright-Fisher model. So sometimes we say that the Wright-Fisher diffusion. So sometimes we say that the Wright-Fisher diffusion is within the domain of attraction of a broad class of discrete reproductive models. And that means we don't need to worry too much about the specific details of the original discrete model that we set up. So how do we describe the Wright-Fisher diffusion? One way that we can do it is as a continuous time, through an SDE. So here is the SDE of the Wright-Fisher diffusion, starting with the Wright-Fisher model that I described earlier. So in particular, this is the diffusion which captures the three processes I am interested in: random genetic drift, mutation, and natural selection. And you can see that it has three parameters: a selection parameter S, which is a rescaled version of the original fitness, a mutation parameter θ1, and a mutation parameter θ2. And these are introducing a deterministic push up or down to the frequency. In SDE parlance, they are contributing to the drift part of the SDE. So if S is a positive parameter, the allele frequency is increasing at a rate proportional to S. If θ1 is positive, then the frequency of the allele I'm tracking is increasing because of mutation to this type, and the frequency is decreasing at a rate proportional to θ2 because of ongoing mutation away from the type that I'm tracking. So selection and mutation manifest themselves as the drift part of a stochastic differential equation. And as it happens, the drift is not too bad. It's linear for the mutation part of the model, and it's quadratic in X for the selection part of the model. The manifestation of random genetic drift is now in the noise part of the SDE. So the random fluctuations over very short timescales being driven by this Brownian motion. This is where genetic drift is coming in, and the Wright-Fisher diffusion has this very characteristic noise term, which looks like the square root of X times 1 minus X. So this is a bit different to a lot of diffusions that other people may have seen, because the noise term will vanish at 0 or at 1. And that means the model becomes entirely deterministic at the point you hit the boundary 0, in which the red allele dies out, or the boundary 1, in which the red allele goes to fixation and the white allele is the one that dies out. And in some sense, we've chosen a time scale, so there is no parameter corresponding to genetic drift. We have chosen a kind of reference time scale so that there are no parameters in drift. And then you can think of selection S and mutation θ1 and θ2 as being the rates of selection and mutation relative to drift. And again, I'm assuming all three of these processes are operating on the same time scale. So this model is suitable for a model of a population in which we need to think about all three of these processes simultaneously. There are lots of versions of the Wright-Fisher diffusion in which you can kind of add further ingredients and get a slightly different description of a diffusion model. So there are Wright-Fisher diffusions which incorporate recombination, which incorporate population substructure and migration, changes in population size, associative mating, all sorts of other processes that you may be interested in, and you can write down a diffusion model to describe it. But this is as complicated as the one I want to study today. Well, I can go a slightly bit further. I can add an extra function, eta, which models frequency-dependent effects of selection. So for example, if I had an allele which was completely dominant or completely underdominant, I would need to tweak the drift term slightly. So I'm assuming I know what the dominant status is, and that manifests as a slight change to the selection function. So this is the model that we want to do inference under, and there are lots of mathematical properties of the Wright-Fisher diffusion that many people have studied, and there's one particular property to which I want to draw your attention, which will turn out to be very relevant later on, when it comes to trying to do statistical inference. And that's the boundary classification of the diffusion. So Feller has lots of well-known diffusion theory, which gives us a way of telling us what's going to happen at the boundary of a diffusion process from its drift and its volatility terms. So from its description through an STE. And you can apply Feller's boundary classification to this model to discover exactly what's going to happen as the diffusion hits one of the boundaries. And we'll only focus on hitting the boundary 0, so the extinction of the red allele, but everything I say applies equally to the boundary at 1 with the other mutation parameter. So if there is no mutation θ1 to introduce the red allele into the population, that means that once the red allele dies out, it can never return. And so if θ1 is equal to 0, there is no mutation rate to θ1 to the red allele. When the diffusion hits the boundary 0, it will stay there indefinitely. And this is known as an exit or an absorbing boundary. It turns out that if the mutation rate is positive, but not too big, and in particular, if it's strictly between 0 and 1, then the classification of the boundary is that it is reflecting. That is, you can hit the boundary, but because of ongoing mutation events, the red allele will be reinserted into the population. And on the timescale of the diffusion, the allele will instantaneously be reintroduced into the population. So the diffusion trajectory is allowed to keep kind of bouncing off of this boundary. And finally, if θ1 is at least as big as 1, then we call the end point at 0 an entrance boundary, which is to say it is not even accessible. The rate of introduction of the red allele into the population is so great that on a finite timescale, the allele can never die out. So you can't even hit the 0 boundary if θ1 is big enough. And you can do exactly the same classification for θ2 and the other end point. And one of the nice things about this classification is that it is independent of the selection parameter. So all of these things are true regardless of what's going on with selection. So suppose we try to do statistical inference under this model. Usually, we would assume we have discrete observations at the fixed times that we dug up some skeletons, for example. I'm going to be generous to myself and pretend that I'm observing the entire sample path for the purposes of inference. So this should allow inference to work better than if we only had discrete observations. This is about as good as we could hope for, and the properties of any estimators that we design from this observation will give us an upper bound on how well we could do if we had noisy and discrete observations of the same process. So I'm going to bundle my 3 parameters into a single object, which I will call phi. So this is the parameterization of the Wright-Fisher diffusion. And I'd like to design an estimator for phi and to understand its properties. So how would we do this? Well, most statisticians at this point would want to write down a likelihood. That is a function of the parameter theta, which is the probability of the data that I actually observed. So I'm interested in the probability of a particular sample path x over time. And we now need to start worrying about some of the technical properties of what a likelihood really is. When we talk about a likelihood, what we're really talking about is what we should call a Radon-Nikodym derivative. It is a probability of a sample path under the parameters that I'm interested in relative to some other probability distribution, some other reference measure or dominating measure. And if we're doing inference, usually the dominating measure will be some fixed parameterization. So when I ask for the probability of the data, what I'm really asking for is the probability of the data relative to some other parameterization. So typically we might say, what's the probability of the data relative to the model that has no mutation and has no selection in it? And that would really be what our likelihood is. So what we're implicitly doing whenever we write down a likelihood is we are appealing to a theorem that says that we can write down this ratio. And the theorem that usually gives us this is called the Gersonov theorem, or the Cameron-Martin-Gersonov theorem, which gives me conditions under which I can write down this likelihood ratio. And one of the key requirements for this to work is that the probability distribution I am interested in is absolutely continuous with respect to the reference measure, by which we mean any event that could happen under the distribution I am studying, under phi, could also have happened under phi 0. What we need to worry about is the possibility that the sample path x is completely incompatible with one of these two measures, and that is what will start to cause problems. So before we can even do any inference, we need to know whether we have this absolute continuity relationship between the two path measures. Are all of the events that can happen under one of the measures also possible under the other measure? That's the key question we need to answer. And just as a quick warning example, it is very easy to come up with models where this is not possible, where you can't write down a likelihood in this sense. Probably the most well-known example is when the parameter is actually governing the noise term, not governing the drift term. If you have a parameter which is governing the noise term, and then you observe the sample path, you do not have absolute continuity between any pair of measures, because observing the sample path effectively tells you exactly what this volatility term is through the quadratic variation of the process. So if we were trying to do statistical inference on parameters of the noise term, we would be in trouble, and we'd have to think of something else. So we're lucky because we don't have any parameters appearing in the noise term. Our parameters are only governing the drift term B, but we still need to worry about the potential for this problem appearing. So one of the main messages of this talk is that you can get similar problems for the Wright-Fisher diffusion, even if the parameter is only controlling the drift term. So the more general question is, if I have three parameters, θ1, θ2, my two mutation parameters, and s, my selection parameter, and I think about different combinations of these triplets, θ1, θ2, s, versus θ1 primed, θ2 primed, s primed, when do we have absolute continuity between these path measures? When can we talk about writing down a likelihood ratio? And when can we talk about having events which are compatible with both of these distributions? And really there's 5 parameters now, because this may also depend on the time horizon t over which I'm looking, and it could even depend on the initial frequency x0 that the process starts with. So we have quite a big kind of combinatorial problem to answer this in full. What do we know already? As far as I can tell, and people who know more about some of these topics can correct me if I'm wrong, we don't know very much for the Wright-Fisher diffusion. For other families of processes, we can find complete classifications. For example, if you were to ask exactly the same question of a Bessel process with its parameter, we know exactly when two Bessel processes are or are not absolutely continuous with respect to each other. But we don't know the answer for the Wright-Fisher diffusion, except for one fairly well-known result, which I think goes back to Dawson in 1978. He was studying a very general measure-valued version of the problem, so this is just a special case of his result. But he showed that as long as you're looking only over a finite time horizon t, and you're only changing the selection parameter, so I'm only changing s here, then the two path measures are indeed equivalent. And furthermore, we can write down the likelihood ratio. So here is an explicit formula for the likelihood ratio in the special case where we're comparing a parameter s to a reference measure, which is the neutral measure when s is equal to 0. And whenever we can write down this likelihood ratio, it will always appear in these models as a kind of stochastic integral of the sample path. So we have to deal with these stochastic integrals, but as modulo the stochastic integrals, we have an expression for the likelihood. So if I was doing inference on the parameter, I could use this expression for the likelihood to design an estimator for S. For example, it's fairly straightforward to find the maximum likelihood estimator for S from an observation of this kind of sample path. In another sense, from a statistical point of view, having equivalence between the measures is bad news in the sense that if I was to observe two sample paths and I ask which one of these is under selection, so suppose I know one is neutral and one is under selection, which one is under selection? Well, if I observe the sample path only over a finite time horizon, because the measures are equivalent, there is no event that can distinguish with certainty between the two parameterizations. So although I can get an estimator, the estimator will never tell me with certainty what the parameter is. So in this example, the left trajectory is a neutral trajectory, the right trajectory is a non-neutral trajectory, but I've only seen it over a finite time horizon. And so my estimator will have some confidence interval that's non-zero. There seem to be few existing results beyond Dawson's, and one of the things I would like to do would be to try to have the same kind of result where we are now allowed to change the mutation parameters as well. And we can make some easy further progress by thinking back to the boundary classifications. So now suppose I observe two trajectories and I ask which one of these two has a mutation parameter which is positive and which one has a mutation parameter which is zero. It's very obvious qualitatively which parameter has θ1 equal to zero. We saw from the boundary classification that if θ1 is zero, the boundary at zero is absorbing, and so it must be the sample path on the left which has θ1 is zero, and the path on the right which has positive value of θ1. So contrary to studying selection, if you observe the entire sample path up to a finite time t, you can be certain whether or not mutation is acting in this model, provided the sample path hits the endpoint at zero. And that means that we do not have absolute continuity between the model with zero upward mutation and non-zero upward mutation. And we can even verify that this relationship fails by giving a specific event which has positive probability under one of the models and zero probability under the other model. And the specific event that tells the difference between these two models is the event that the diffusion spends some positive time at zero for some interval over the time horizon. So this event A has positive probability under one model, zero probability under the other, and that is what is contradicting the absolute continuity relationship. Just thinking about boundary classifications does not get us all the way there. For example, suppose I was looking at two different parameterizations which had two different upward mutation rates. So θ1 and θ1 primed. They're both between 0 and 1, so they're both reflecting boundaries. But do I have absolute continuity or not? Well, qualitatively, it looks like they have the same kind of sample paths as you observe them hitting the boundary at zero. It turns out that, and this is part of one of the results I'll present soon, that we still do not have absolute continuity between these two models. And what's really happening is the noise term of the model is going to zero. The model is becoming deterministic as you hit the boundary. And the deterministicness of the model is allowing you to observe really what the parameter θ1 is. So because it's becoming deterministic, it's looking more and more like an ordinary differential equation near the boundary. And something like the angle at which it hits the boundary reveals what the parameter θ1 is. So we can't really talk about an angle because it's a diffusion, but some property of the way that it is hitting the boundary is revealing the parameter without error. So we would like to give a complete classification of when this happens and how this happens. And the way I'm going to do it is to use the notion of what's called separating times. So this gives us a very fine-grained way of describing how absolute continuity between two diffusion paths are lost. So I'm going to give a couple of abstract descriptions now, and then later on we will discover what the separating times of the Wright-Fisher diffusion are. So a separating time is an extended stopping time, and an extended stopping time is just a usual stopping time, but I'm going to add on to my time axis, which goes from 0 to infinity, an additional point, which I'll call delta, and that additional point I'm going to think of as coming after infinity. So this idea goes back to Cherney and Urasov in 2006. And the idea is that the diffusion paths may be absolutely continuous for any finite time, but they could separate at infinity, or they could never separate. And I need to be able to distinguish between those two possibilities. So I need an extra time point after infinity. So what I'm going to say is, if my two diffusion measures separate at infinity, then they're okay for any finite time, but not for any infinite time. If they separate at delta, then they never separate, even if I observe them from an infinite time horizon. So an extended stopping time is just our usual stopping time, except it can take the value delta. And then I can define a separating time. So I'm going to call a time separating one measure parameterized by phi2 from another measure parameterized by phi1 if it appears as if the two measures are absolute, or one measure is absolutely continuous with respect to the other up to any extended stopping time prior to the separating time, and the two measures become mutually singular after the separating time. So we can think of the separating time as a random time before which the two diffusions look as if they may be absolutely continuous, before which they are absolutely continuous, and after which something has happened which makes the two measures singular. So S is a random time, and that's the object whose distribution we would like to describe. I can take the definition a bit further, I should say. We can also talk about mutual separating times, which is a kind of a commutative version of the same definition, in which before the mutual separating time, the two measures are equivalent, they are absolutely continuous with respect to each other, and after which they are singular. And the results of Cherney and Urasov show that separating times exist under certain conditions, and they are even unique under the measures we are studying. So very briefly then, any concepts that you are familiar with when we think about the arrangement of different probability measures can be described through their separating times. So equivalence of measures is the same as saying that the separating time is delta. Mutual singularity of measures is the same as saying that the separating time is at most infinity, and all sorts of other relationships we can describe in terms of separating times. So what are the separating times for the Wright-Fisher diffusion? That's the main question. And I claim that the separating time in our absorbing example turns out to be precisely the hitting time of 0. So it really is the time at which you hit 0 where you can tell precisely what the value of θ1 is, and you can't tell precisely before that time. If we look at the reflecting example, it's harder to tell how you can separate the two measures for this one, where they're both reflecting but under different parameters. It turns out that the separating time for this pair of models is again the first hitting time T0 of 0. So I think I'm going to skip some of the details, which is about how we prove what the separating time is. But it relates to the proof method uses, I will just use the keywords, the occupation times formula and characterization of local time in terms of speed and scale. But I don't think I'll say any more about that. So here's the main result, which now we go back to our Wright-Fisher diffusion, and we have all sorts of combinations of parameters that we need to think about. But I think I have been able to characterize all combinations down to a single table that I could fit onto one slide. And this tells me what the separating time is. So the key entries in this table is the last column, which is what is the distribution of the separating time. And the answer is, depending on the parameters, the separating time is always given. It's always either delta or infinity or some function of the first hitting times of the boundaries. So in the interior of the state space, when the allele frequency is at intermediate frequencies, there is never any separation. You may get some separation if the diffusion hits the boundary. So just to give a couple of examples to see that this table makes sense, the first line of the table, what's this saying? Theta1 can take any value, theta2 can take any value. The mutation parameters of the other measure are the same, and the selection parameters are the same. So this is the special case where all parameters are the same, and the separating time is obviously delta. The two measures never separate. I've picked out this example again as well. So what does this say? Theta1 is 0, so the 0 boundary is absorbing. Theta2 is at least 1, so the boundary at 1 is inaccessible. Theta1 primed is also absorbing. Theta2 is different from Theta1, and the selection parameter is different as well. And this tells me that the separating time is still delta. So how do I interpret this? These two models might only differ at Theta2. Theta2 will only be revealed if I hit the boundary at 1, but the boundary at 0 is absorbing. And so in any finite time, I'm going to get absorbed at 0 before I have a chance to hit the boundary at 1. So there is never an opportunity for the parameter theta2 to reveal itself, even though they're different under the two measures. The separating time is therefore still delta. All right, I'll do one more example and then I'll start to wrap up. So what's going on here? Both boundaries are absorbing under one model. Theta1 and theta2 are 0. Theta1 primed is different. Theta2 primed is also absorbing. So what's going to happen under this pair of models? I observe a trajectory, and the trajectory will either get absorbed at 0 or it will get absorbed at 1. If it gets absorbed at 0, then the difference in the theta1 parameter will be revealed and the two measures will separate at time 0. Otherwise, if I'm absorbed at 1, there is never an opportunity for me to reveal the difference in the theta1 parameters, and the two diffusions will never separate. So we can go through all of these cases. It covers everything, and the upshot is that the measures may or may not separate depending on the parameterization. A further result is that we would like to find some event which has positive probability under one of the models and 0 probability under the other model. And it is possible to find such an event. So here is a result which says that in my reflecting example, I know the two measures are going to separate, but I don't know exactly how they separate. This result tells me how they separate. And what it says is, if I observe the trajectory as it goes to 0, I should compute this quantity, the limit of log x over some path integral of x, up to the time that I hit 0. And this quantity, it turns out, will converge with probability 1 to theta1 minus 1 over 2. So in other words, if I observe the trajectory and I compute this particular object from the trajectory, this tells me exactly what the parameter is. And so this event will have probability 1 under theta1 and probability 0 under any other parameterization. So we can even find the events. We can tell how to look at a trajectory and to extract the parameter from it as it hits the boundary. And again, there are some analogs with the Bessel process. So when I was doing this work, I was looking a lot at the literature on the Bessel process, where we have identities like this already. But as far as I can tell, we didn't really have anything analogous for the Wright-Fisher diffusion. Okay. Yeah, all right, I'm going to skip some of these. So we have a few other results as well relating to these. So the last thing I want to say really is about statistical inference. What does the separation of measures tell? How does it have implications for doing statistical inference? At least up to a separating time, we can write down a likelihood ratio for two different parameterizations. And we can even get an expression for it using the Gersonov theorem, which again, it will be a stochastic integral of the sample path up to time t. And in principle, I can do the usual manipulations of this likelihood to try to get an expression like a maximum likelihood estimator. So I can take this object, I can take a logarithm, differentiate with respect to the parameters, set to 0 and solve it. And in principle, I get a maximum likelihood estimator for a given trajectory. But I know that something is going to go wrong with this expression if the diffusion hits one of the two boundaries in finite time and the dominating measure and the measure of interest disagree with each other in certain ways. So how does the estimator, in particular, how does the maximum likelihood estimator behave in light of the fact that the two measures might separate from each other? So to illustrate this, I'm going to write down what the maximum likelihood estimator for the mutation parameters is under the assumption that the selection parameter is known. So this is quite an ugly expression, but I want to kind of emphasize where it came from is very straightforward. It really is just differentiating a likelihood, setting to 0 and solving. We get some expression for the maximum likelihood estimator of the mutation parameters, and it is a function of some path integrals relating to the trajectory. And I know how these path integrals behave as they hit the boundary. In particular, some of these path integrals will converge to the value of the parameter I am estimating. They will converge to θ1 specifically, or some function of θ1. So what happens is, some of the terms in this maximum likelihood estimator will explode, and some will go to 0, and it will explode in such a way that the maximum likelihood estimator of the parameter converges to the truth with probability 1. So a statistician would say that this estimator is strongly consistent. It's even better than strongly consistent. It's strongly consistent in finite time. So the separation of the measures has manifested itself in terms of, in statistical inference parlance, by giving us strong consistency of the estimators. Hitting the boundary reveals the value of the parameter as it hits the boundary, and our estimators automatically converge to the truth and give us the exact parameterizations with 0 error. Yeah, okay. And we can get all sorts of other sorts of law of large numbers results and central limit theorems relating to the behaviors of the parameters, depending on different parameterizations. So I think I'm at a point where I can start to wrap up. To summarize some of the key things I've said, the Wright-Fisher diffusion plays a central role in modeling evolution and modeling changes in allele frequencies over time, whenever genetic drift cannot be ignored. And I was really happy when I discovered this work by Cherny and Urasov on separating times. They really provide, in my opinion, a coherent description of the relationship between two diffusion path measures. And we can calculate them explicitly for the Wright-Fisher diffusion. And I found a few examples of separating events which testify to separation having occurred. I should also say, you know, I can feel people bristling because this really has another message underlying this, which is, is this really what happens if we're modeling a population? In reality, a biological population is a discrete object. There are a discrete number of individuals, and it's not a diffusion evolving in continuous time. So would we really observe this happening in a real population? What we found is that the Wright-Fisher diffusion has taken on a life of its own, in the sense that we can study this really interesting boundary behavior of the diffusion. It could be accessible or not. It could have vanishing noise. We get separation of path measures, and we get perfect statistical inference. So as a model, this is great for learning the parameters. But you know, many people would argue it is an approximation to a real population, which is finite. And if you were to do all of the same kinds of calculations for a discrete time, discrete space reproductive model, you may not get the same kinds of issues. So it's with a very heavy heart that I say this, because I really enjoy studying the Wright-Fisher diffusion. But we have to be very careful when using it as a model about some mathematical properties of it, which may not you know, fully capture what's going on with the real population. So there, I've kind of anticipated the first question, I hope. I was very pleased about kind of noticing this, and then I found this comment in the book by Ewens, who says, "We observe in conclusion, diffusion theory can give quite a false impression, not only quantitatively, but also qualitatively, about the boundary behavior of some Markov chains." So Ewan's clearly has noticed this long before I did. So I guess another message of the talk is that we should all read Ewan's. I should say this kind of issue, separation of path measures, can happen under other models. I have a paper with Bob Griffiths about the same kinds of issues when we study estimators of recombination. And there's a really nice paper that I discovered by Overbeck, who shows that you get the same kinds of problems if you're trying to estimate the immigration parameter of the CBI diffusion. So it does crop up in other places as well. I think I'm out of time. This work is still on archive. I keep meaning to put it on archive, and it should appear very soon. I've had very productive conversations with Bob Griffiths, Alex Mijatovic, and Dario Spano, and many others. So thank you very much for your attention.